Sì, ma è veloce. Ci siamo? Dare inizio a questo pomeriggio interessantissimo della presenza della fratello è un piacere e un onore per me avere Filomena qui con l'aula dell'innam quasi piena. Filomena, diciamo che non ha bisogno di presentazioni, ma gliela farò, spero, bene. Professore ordinario dal 1990 all'Università di Roma La Sapienza, ma prima, ben po' prima, è stata ricercatore presso l'Università degli Studi di Napoli Federico II e io la conosco veramente da molto tempo. È tra i principali esperti, come tutti voi sapete, di analisi lineare, equazioni delle derivate parziali. La sua carriera vanta tantissimi successi, tra cui collaborazioni con personaggi di spicco nell'analisi matematica, posizioni per i professori visitatori presso le più prestigiose università europee e non, come Parigi 6, Paris Dauphine, Current Institute, Rutgers University, University del Wisconsin. Non le elenco tutte evitando di commettere errori o dimenticanze. Anche dal punto di vista, diciamo, anche i seminari sono numerosissimi, conferenze su invito, PTH di Zurigo, plenary talk al Summer Workshop in Brasilia, più volte a Oxford, Mittag Leffler, più volte a Oberwolfach, e poi vanta diciamo, tra i suoi allievi dottorandi e postdoc persone che sono, diciamo, si sono affermate nell'ambito accademico e anche editore, partecipa, diciamo, all'editorial board di numerose riviste. Per me quindi è un onore presentarla qui e il titolo del suo seminario è Mean Curvature and Soap Balance. Prego Filomena, grazie per averci accettato.
Grazie Cristina della bellissima presentazione. Io parlerò in inglese, ma questi ringraziamenti li posso fare in italiano. Sono molto contenta di essere qui, da un istituto prestigioso, quindi mi fa molto piacere che il comitato scientifico mi abbia proposto, di onorare di questo. Vabbè, Cristina ci conosciamo come ha detto lei, diciamo, vabbè, diciamo che era una bambina quando io già okay, so let me switch to English. I like to give this colloquium because it gives me the opportunity to speak about some simple classical problem, which which is very interesting in mathematics in general. So something which is in between analysis, geometry, mathematical physics, or whatever you want to say. So I will speak about the main curvature, in particular constant main curvature surfaces. And obviously you can, I could speak for hours, for days about the curvature. So I have decided to take a path which goes through compact higher surfaces in order to show both some classical results and some very old classical results and some new development. Okay, so let me start then with so then you will understand why the top bubble theorem enters into the name of my talk. Yeah. Okay. Okay. Okay, so the first part, let me speak about closed higher surfaces, which means a compact and without boundary. Okay, so let us see what we have in mind. No, parecchio. Però devo usare quello.
No, 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 no. No, posso... No, ok.
No,
Ok, no, no. Ok.
Okay, so let me start with a very classical simple question. So let us consider a connected closed between compacted without boundary, smooth, at least let's say C2, hypersurface, which means
No,
sorry, ma io non ho fatto nulla.
no, no, no. No, sorry. No.
Adesso vedrete tutta la torre. Che è successo?
No, avevo semplicemente indicato perché si era...
Vabbè, ma adesso che devo fare? Ripartiamo da capo, vabbè. Okay, so we are speaking about okay, so closed means compacted without boundary, hypersurface means codimension 1 and -1 dimension embedded in Rn. Okay, so a classical question is this one: if M has a constant main curvature, which will be CMC in short, is it a shear? Okay, so it's a very, very good question. And there is a theorem that was written by Jellett in 1853, which, for what I have understood, for what I have found, is the first answer to this problem, but in a particular setting, in the setting of star-shaped hypersurfaces. So you can see this is a very short proof of 4 pages in 1853. So what is star-shaped? It means that Jellett was considering M as the boundary of a bounded domain in Rn, which is in our way of saying is strictly star-shaped. That is, we require that X that the exterior normal is positive all over the boundary of this set omega, which is indeed M. Okay, so equivalently, you can say that the boundary of this set is the polar graph of the smooth function on the unit sphere. Okay, so what is why the proof of Jellett was so simple? So it is based on PD and the maximum principle. So we will see in a moment the proof, because I like, since not many people know this proof, I like to give at least a sketch of the proof. And in fact, Jellett's result was not so well known. I have learned from a colleague of mine, but in the context of CMC is not much well known. In fact, I think it's more known a later result by Lieberman, which is a weaker result because it applies only to closed convex hypersurface. So let us see what is Jellett proof. So Jellett proof is very easy. It considers 2 functions. So the first function is just the distance from the origin of a point in the manifold, and this is just a scalar product. If you compute the Laplace operator of psi, you end up with this formula, where h is the mean curvature, so n minus 1 times h is just a trace of the second fundamental form. Then I compute the Laplacian of the second function of lambda, and you get then what one needs at this point is to recall this classical matrix inequality, which compare the square of the matrix corresponding to the second fundamental form to the trace of h. And then if you just subtract the 2 Laplacian, you get that the Laplacian of the difference of h times psi minus lambda is equal to this expression. And if you use that this scalar product is positive, you get that h times psi minus lambda is a subharmonic function on a closed manifold. So this means that it must be constant. So, and because lambda is positive, to be constant means that the Laplacian is 0. And so you get this identity. So if you get this identity, it means that you have equality in the matrix inequality. So which means that your surface is, as what you say, is umbilical. So it means that the second fundamental form is just a multiple of an identity. Okay, so this is the simple proof. Just 2 pages, as you can see, is maximum principle, essentially. Okay, so the story continues, and in fact, the problem was completely solved only 100 years after Gellet by Alexandrov. So if you look at in Google, you see that these 2 dates. So they correspond to papers which were written in Russian. So I think it's probably it was the first version, and then it's usually it appears within 1958. Then there is another version in English, was in 1962. So Alexandrov proved the theorem in the full generality. So it's called the soap bubble theorem because it characterizes the bubble that you blow when you play with the soap bubble. So any smooth closed connected CMC hypersurface in Rn is. Okay, so the proof of Alexandrov is very much different from the one of Gellet. The one of Gellet cannot be really extended to things which are not star-shaped. So it consists in showing that if H is constant on M, on the surface, then M must be symmetric with respect to any hyperplane passing through a fixed point, and therefore this point must be the center of mass of this surface, so it's a center of a sphere, and I mean the surface is a sphere because it's invariant with respect to generators of the orthogonal group in Rn, so it must be necessarily. How does he prove this? He proves these symmetry properties of the sphere by really with a very ingenious proof. A very ingenious proof because it introduced for the first time in PDE a reflection method, which since then is known as a moving plane method, which is entirely based on the maximum principle, but it's far more sophisticated than the simple proof by Gellet. This method was so beautiful, so intuitive, so strong that was later was used in plenty of symmetry results in PDE. In particular, let me quote the 2 famous papers by Serren for an overdeterminate problem and Didassi and Nirenberg for symmetry of solution of nonlinear equations. Okay, so as it happens, when somebody finds the proof, then immediately other proof will get enlightened, and so almost not too late, let's say, if you think that from Gellet proof to Alexandrov it passed 100 years, but after a few decades there were other proofs, so which were actually shorter and easier than the proof of Alexandrov. So one is usually named after Rayleigh, but the person who contributed to understand that an identity in Riemannian geometry called the Rayleigh identity could be used to prove the soap bubble theorem was Alexandrov, as far as I have understood, and which also use a PD approach. I will tell you in a moment what it is. And then there was a more geometrical proof by Montiel and Ross. Anyway, both proofs relies on the fact that after identities, after manipulating something, you reach identity in the matrix inequality that I showed you before. And so then this means that the surface is a sphere. Okay, so the approach of Rayleigh, what is it? It's simple because you consider this simple PD problem, this Poisson problem, minus delta U equal 1 in omega. So you have a condition. Then, if you apply this identity, this Rayleigh identity, to the solution of this equation, you end up again. So I'm shortening, but really the proof is quite short. You end up again with this identity in the matrix inequality. Okay. So what is interesting is that prove this simple Poisson problem, which apparently has nothing to do with the constant and curvature surfaces question, you reach the soap bubble theorem. And in fact, one could see that an intermediate step in the proof of Rayleigh and Ross shows that, in fact, if you apply this identity, you can prove that the normal derivative of the function u of this Poisson problem is constant on the boundary. Okay, so there is a relation between the soap bubble result and the result which allows to say that if you impose an extra boundary condition here, an overdeterminate condition, then the domain must be a board. And this is, as I was telling you before, this is the beautiful result of Serrin. So, following this proof, you could deduce the soap bubble theorem by the Serrin result. Let me tell you, and this I will probably, if I have time, I will say it also later, that we have seen that in a sense CMC implies overdeterminate. The vice versa in general is not true. And the overdeterminate problem is a PD problem, which is, in my opinion, more sophisticated and more difficult than this constant and curvature question. But anyway, there is a relation between the two, and it's still an open question to understand a precise relation between these two problems. Okay, so let's go ahead. So I don't want to speak about non-compact. Everything will be about compact surfaces. I just want to show you that if you go out from the compact setting, then you may have a lot of CMC surfaces. And in fact, you could, for example, in 1841, Delaunay had constructed several revolution constant mean curvature surfaces, which were non-compact, unless, of course, you consider also the sphere as a surface. So this, for example, is a minimal surface, and these are other surface of a revolution they constructed in R3. So this is just to say that there are several CMC surfaces, and actually then a lot of mathematicians have played in constructing other surfaces by this one, just gluing together some pieces of these surfaces. Okay, but so we go back to the setting of the compact surfaces. So my aim later will be to speak about surfaces with boundary and to see whether we can ever characterize the surfaces with a boundary, compact surfaces with a boundary. So before doing this, just to see what comes after, let me say that the soap bubble theorem can be considered as a more general result with respect to another very beautiful classical symmetry result in mathematics, which is the isoperimetric property of the sphere. So what I want to show you, to the aim of introducing what happens for surfaces with a boundary, is I want to explain what is the relation between these two symmetry results. Okay, so let's see. Okay, what is the isoperimetric problem? So we consider a measurable set in Rn with the finite measure, and let's consider the perimeter of this set, which is usually called the Georgi perimeter. Okay, for me, everything will be smooth, so don't worry about knowing or not knowing perimeters and so on. Let's think just about the measure of a smooth boundary of a set. Okay, so the classical isoperimetric inequality is this one. It tells you that the perimeter of a set E is greater or equal than an absolute constant, which depends on the dimension. Cm is the measure of the unit ball in Rn. And here there are some powers which makes this inequality dimensionally consistent. For every set with a finite perimeter, of course, if the perimeter is not finite, of course you have this. But the interesting thing in this isoperimetric inequality that you get equality if and only if E is a ball. Okay, so this gives you the characterization, the rigidity result, which characterize the ball as the one which for which the equality holds, which means that balls are the only set which minimize the perimeter with a fixed volume. So in this generality, with the definition of a perimeter, it was proved by Ennio De Giorgi in 1958. And his proof reminds a bit just in spirit of the one of Alexandrov, because he wants to prove, and he proved, that in fact the sets which were reaching equality, the supermetric inequality, must be symmetric with respect to any other. So he used the first Steiner symmetrization with respect to an hyperplane to prove that the perimeter is strictly reduced when you have something which is symmetric with respect to the Steiner symmetrization. Then I'm quoting Gosserman, which gave another nice proof. It's in this paper in 1978, but probably was also known before, where instead he used another definition of measure of the boundary of a set, which is the Minkowski content, and he used the Minkowski inequality in order to prove the property, the isoperimetric property of the ball. And then in the book of Federer, you can find some other results. But anyway, after that, probably most of you know that there are many other proofs of the isoperimetric inequality. I will recall some later when I will speak about the surfaces with the boundary. Okay, so what is the relation between the constant domain curvature surfaces and the isoperimetric inequality? So I'm mentioning this because through the perimeter function, we can have a variational formulation of the constant domain curvature problem. Why? Take the functional, the perimeter functional. You can take the derivative of this functional with respect to variation of your set E, which leave the measure of the set fixed. Okay, so then if you do this operation, and because you have a constraint, which is the measure, which is a volume constraint, then you may use, in order to characterize what means critical points, you use a Lagrange multiplying rule, and one can prove that in fact a critical point of the perimeter functional with respect to the volume constraint is indeed a surface which has a domain, whose boundary, the boundary of this set, is a surface which is has a constant domain curvature, of course, on the regular part of the boundary. Okay, so there is so this means that Alexandrov theorem, as I was telling you before, is more general than the isoperimetric property of the sphere, because it characterizes the ball or the sphere among not only among the minimizers for the perimeter, but also for the critical point. So Alexandrov theorem is more general, but it was done for smooth surfaces. Recently, a nice proof, how do you say, a nice version of the Alexandrov theorem for set of finite perimeter was given by the Galdino and Mangi. Okay, so CMC is more general than isoperimetric problem. Okay, so let's now shift.
So in the last result, there is no assumption on regularity. Just take critical points.
Finite perimeter.
Just finite perimeter.
Finite perimeter.
And the regularity.
And yes, the regularity is no. In the last del Galdino Mangi.
Yes.
No, it's not smooth. They prove that they put the assumption the regular part of the boundary has constant domain curvature. Because a set of finite perimeter, you can divide the boundary into parts.
Yes.
And then at the end, of course, if it's of course, at the end it is of course it is.
But it's start with
Actually, you prove that since you are critical, if you don't put the positive connected, you can have a finite number of balls with the same radius.
No, not about connectedness.
Yeah. Okay, so now let's shift to surfaces with a boundary. So compact hypersurfaces with a boundary. Okay, so let's say this. Let's mention this a bit silly question. Can we characterize them in some way? Of course, I'm speaking now about a mathematical problem, a mathematical object with a boundary. So if I don't put some boundary condition, I don't get anything. This we know from since the beginning of the problem in mathematics. So let us understand what kind of reasonable boundary condition we can put, in what context we can formulate this question. Okay, so I will speak about a context which is the one of considering hypersurfaces in cones. Okay, why? Okay, I will give you a few motivation for that. But first one can be just, let's say, by analogy with what we have for closer. Suppose now that instead of characterizing a sphere, I want to characterize a portion of a sphere as the only compact surface with boundary which does certain things. Then I should be in a radial setting in order to be able to consider this kind of surfaces. So this is one simple reason to say, okay, let's consider a cone. Okay, so let us see what I would like to present. So I have so now instead of considering the surfaces which are free to move in the whole Rn, so let me consider a cone in Rn. So a cone, actually a positive cone, which is just of course something which is spanned by a domain D on the unit sphere. Okay, so this is a cone, several cones. This is a kind of ice cream cones, but the D could be something different. Okay, of course the pictures are not extremely nice. Okay, so now I want to consider surfaces which live inside the cone. So I would consider gamma. So it has a boundary, and I put the restriction that the boundary of gamma must be on the boundary of the cone. Okay. This surface gamma, here is just a spherical cap, for example, or here I have another surface, I mean, could be in different position inside the cone. They could be considered as the relative boundary of a domain inside the cone. Okay, so if omega is domain inside the cone, I can divide this boundary in two parts. One part, which is the one inside the cone, which is called the free boundary of the relative boundary of the set, and another part, of course, which is the blue one, which stays on the boundary of the cone. So in particular, we could have a spherical sector, so the intersection of a ball with the cone, and then of course the relative boundary, the free boundary, is just a spherical cap. Okay, so the question now is that I want to pose starts first of all by this observation. Okay, this looks like an ice cream cone, but think about a cone of any shape. If you take a cone of any shape, and then you take the intersection of the sphere with the cone, you can observe, it's very easy to say, with the vertex in the vertex of the cone, with the center of the sphere in the vertex of the cone, then it's very easy to see that the spherical cap intersects the cone orthogonally. Okay? So then let's try this boundary condition. So let's try to see if I can characterize the constant Minkowski surfaces inside the cone, which intersect the boundary of the cone orthogonally. So can we claim that they are part of a sphere, so a spherical cap in my definition, in my way of saying it, centered at the vertex of the cone. So if I have this, then I could say that I get a sort of bubble theorem for surfaces with a boundary in this setting. Okay, you blow up a bubble, but you don't blow very strongly, so the bubble remains attached to your frame, and then in fact you can see this. So I have never tried with very strange frames to see if you get something else, but usually you get a portion of a sphere. But okay, anyway, let us see in the mathematical context what we can prove. Okay, so first of all, let me make a comment on this orthogonality condition. So now I have motivated it just saying, okay, because the pieces of a sphere have this property, this orthogonality property, let's try with this one. But there is a much deeper and intrinsic motivation to have this orthogonality. Let's see what it is. In order to show you this and to see why one has in mind this boundary condition, let me give a variational formulation also here of this constant mean curvature question. So again, I want to give a variational formulation in terms of critical points of the perimeter function. So now the perimeter, it has to be understood in a relative setting. This was something which was already defined by the Giorgi. So if we have a set in the cone, but also in other sets anyway. So the part of the boundary which is inside the cone is called the relative boundary. So the relative perimeter, it just measures this part here. Okay. So again, as before, I look at the variational method. So what does it mean? I take this relative perimeter function. I take the derivative with respect to variation of my domain, variation of the domain which leave the cone invariant. So this means that I have to get a smooth deformation with respect to vector field which are tangent to the boundary of the cone. And then, of course, I do not want to change the measure of the set. So then, if I do this, it's not difficult to show that if the domain E is a critical point of the relative perimeter function with this volume constraint, this is equivalent to say that the relative boundary is a constant mean curvature surface which intersects the boundary. So this is the natural condition if you want to have a variational formulation of this problem. Okay, so again, so if ever I succeed in characterizing the constant mean curvature surfaces which hit the boundary of the cone orthogonally, it means that I have characterized the critical points of this perimeter function. Among the critical points, there are the minimizer. So let's first try with the minimizer. Trying with the minimizer, it means to have an isoperimetric inequality. Okay, if I want to characterize the minimizer, it means that I am thinking of an isoperimetric inequality. What does it mean? That I'm thinking of having this relative isoperimetric inequality in a cone, which tells you that the perimeter, relative perimeter is always greater or equal than this absolute constant, where now this is, of course, the measure of the unit ball intersected with the cone, the unit spherical sector, times the measure of the domain. And I would like to see that the quantity holds if and only if this time this is a spherical sector. This is true, but I have to add this condition that this is a convex cone. So in convex cone, we have a perfect analog of the isoperimetric inequality. So we have a characterization of the minimizer of the relative perimeter with a volume constraint. Okay, when this isoperimetric inequality was proved in 1990 in a paper by Pierre Williams and myself, and let me say immediately that we could not copy the proof of the Giorgi. If you want to try anything which gives you that the surface should be symmetric, you don't get anything, because inside the cone, the cone can have any shape, what kind of symmetry you can consider. So we have extended to our case the Bruni-Minkowski inequality, so let's say the approach of Osserman. But later, the same isoperimetric inequality in convex cone was obtained by Ritoré and Rosales in, let's say, differential geometry, also considering the sets in manifold, by a calculus variation method, in the sense that they were able to characterize the stable critical point of the perimeter function. Then there was a proof by Figalli and Trey in 2013, when he used this more modern technique of optimal transport, and they also obtained a quantitative version of the isoperimetric inequality in cones. And then another beautiful proof which used PDE, a Neumann problem in PDE, was given by Cabrero, Sotone, and Serra. Okay, the interesting thing is that all these four proofs, they are completely different one from each other, but for all these proofs, the convexity of the cone is absolutely necessary. Okay, so what if the cone is not convex? Many years ago, in a personal communication, when I was speaking with the Georgie, which was a very nice person, apart from being an excellent mathematician, he was a very nice and encouraging person. So I was in Pisa once for a meeting, and then I spoke to him about this isoperimetric inequality. And then asked him whether he was thinking that in a non-convex cone he could do it. And immediately said, oh, okay, if you perturb a bit the convexity, then it should be true. And so this is not a closed, let's say, set of... and then many years later, I reported this to Alessio Figalli, and then quite quickly, in a few months, he gave a proof of this, let's say, conjecture, simple conjecture by the George. In a sense, so if you take a convex cone, you can perturb a bit it, and then you still have this isoperimetric property. But anyway, when we started with this argument many years ago with the Pierre-Williams, what we had in mind was not so much the geometric problem, not so much the constant curvature surfaces, but we were motivated by introducing a symmetrization technique that was able for problems where on the boundary of the problems you did not have a Dirichlet condition, but you had a mixed boundary condition. And this was something that I was studying at the time together with Pierre-Williams and with Maria Rosaria Tricarico, who is a dear colleague of mine who just passed away some few months ago. Okay. So, so now let's go ahead. So we have a rigidity resulting convex cone, and then let's shift to constant mean curvature surfaces which intersect the boundary with the cone orthogonally. Is it possible to characterize them? So after the isoperimetric inequality, we would think that at least in convex cone this should be done. And in fact, this is true. And actually, it is true even if you have a more general boundary condition, which is given in media, let's say, in an integral form, as a scalar product between x on the surface and nx, which is the outward unit conormal, so it's to the boundary of the surface. Of course, when okay, not of course, but it's very easy to when you have orthogonal intersection, this is always satisfied. This is equal to 2. This is interesting because, as I told you, if you look at the constant mean curvature surfaces, you may have plenty of them. You have cylindrical surfaces, you have Zeroni surfaces, you have onduloids, catenoids, and so on. Then you can take one of these and you insert it inside the cone. So they are not spherical surfaces. Okay, in particular, if you take the catenoid size, this is a minimal surface, so that cannot have a curvature which is positive. So it means that we will never satisfy this. So you can put it in an aspirin cone and you will never satisfy it. So this is I think it's a nice condition. So who proved this? It was proved by Cho and Park in 2011 and by Brown and myself in 2020. Actually, we did not know this proof that there was an existing proof, and our proof was similar to the one, except that we were it's based on the Rayleigh-Ross argument. And okay, our was more general paper because we were also showing that we could obtain this through the Montier-Ross argument and also through the other determinate problem. But anyway, I mean, the Rayleigh-Ross proof was exactly the same in this paper. Okay, so as I was saying, the convexity of the cone now is crucial, in particular in this soap-bubble theorem. Okay, so then you may ask immediately, okay, but of course, if Bayer and Figalli succeed in relaxing this condition, then it should be true also for constant mean curvature surfaces. If you take an almost convex cone, then it should be true. I was not able to prove it, Giulio Tralli was not able, other people who were speaking were not at all able to do this. The Bayer-Figalli proof was relying on the fact that really you had the minimizer. The minimizer go to minimizer when you move a bit something, but for constantly incorporated surfaces, we could not do it. Okay, so in the last part of my talk, now I would like now to see and to show what can happen in non-convex cones. Okay, so what could be interesting in non-convex cone now, it would be to show that it is not true that you have this characterization in terms of spherical surfaces, which you may expect from what I was telling you before, but also to show that there could be probably many more compact hypersurfaces, and which are not probably the known one. Okay, let us see what we can do. Okay, so what we have in mind? We have in mind two questions. So existence of non-trivial compact constant main curvature surfaces with boundary. Okay. And the second question, motivated by what I was telling you before, what class of a non-convex cone we can consider? Can we characterize the non-convex cone which do not have isoperimetric property? Okay, in order to do this, so what we do is we study closely the trivial constant main curvature surfaces, which are given as spherical cap, to see why they lose this isoperimetric property, why they are not anymore minimizer, the boundary of minimizers. Of course, they are always critical point of the perimeter function, just because they intersect the cone orthogonally and are constantly curvature surfaces. So they are critical points. Why they are not minimized? What happens when they are not minimized? Okay, so in order to do this, so what we have, I mean, the simplest, most direct approach is to study. We have a critical point of a function, and you want to see why this critical point is not minimized. So what you do, you study the second derivative, and you try to see whether this critical point is stable or unstable, and when it becomes stable or unstable. So this is exactly what this is exactly the project. So this is exactly what I'll tell you what is the result in a moment. So in order to study the so we want to study the critical point of the perimeter functional, which corresponds to these trivial critical points, which are the spherical surfaces. And we want to see why they lose the property of being a minimizer. Okay, in order to simplify the problem, if you write down the second derivative in general, can be complicated, but we make a very simple observation that my surface, my spherical surface, can be seen as the polar graph of a constant function on the sphere. So when you want to study the property of a critical point, you have to perturb, let's say, the Hessian matrix locally around the point. So I just perturb a bit this. So if I perturb a bit this means that I can just consider surfaces which are the graph of a function on the sphere. And this is easier. Why it is easier? Because a graph can be defined like this. Phi is a function, smooth function on the domain D which spans the cone. And this is the hypergraph of this graph. So this is much nicer because I can parameterize my perimeter functional considering the function phi, which are a function on smooth function on D. So another reason is that, of course, if you have an hypograph, then it's very easy to write the perimeter functional. The perimeter is the measure of a graph. It's very easy to write the volume, and you have this two form. Okay, so now let us remember that we don't want the free critical point of my functional, but we have to impose a constraint. The constraint is the volume. So I have to consider a manifold inside the Banach space of a C2 function on the sphere, on the domain of the sphere, for which the volume is fixed. So I have fixed the volume corresponding to the unit spherical sector. And so this means that I have to take the deformations which are tangent to this manifold. So what is the tangent space to this manifold? The tangent space to the manifold of the volume constrained critical volume constrained hypograph is given by this expression. So what I do, I consider the restriction of my functional on this manifold M, and I investigated the second derivative, which is a bilinear form, in the direction which belongs to the tangent space. Okay, so when I do this, now this was in general for any graph, but I am just analyzing what happens in the trivial graph. The trivial graph is given by the function phi identical equal to 0. So then when I do this, you plug phi equals 0 in your expression, and you just, the bilinear form has a very nice expression. And if you look at the quadratic form, you see there is a Dirichlet integral. So this suggests you what you have to do. So what you have to do in order to study the stability or instability, you have to look at the tangent space to the manifold given at the trivial point phi equals 0. And this is just the function on the sphere, on the domain of the sphere, which have a mean value 0. And then this fact, together with the expression of the second of the quadratic form corresponding to the second operation, suggests that what you should do, you should consider the Neumann eigenvalue, the Laplace-Beltrami operator of the sphere. Why? Because the first non-trivial eigenvalue is just obtained as the infimum on the tangent space. So this means that you can span every element in the tangent space as a Fourier series of the eigenvalue of the eigenfunction of the Laplace-Beltrami operator of the Neumann eigenvalues. Okay, so then if you do this, you end up with this result, which was obtained by Alessandro Jacopetti and Tobias Wett and myself 2 years ago. And so this is why this first eigenvalue, first non-trivial eigenvalue of the Laplace-Beltrami operator in the domain D with the 0 Neumann condition enters into the picture. So we could have a precise characterization of the minimizer, the local minimizer. If this eigenvalue is smaller than n-1, then the spherical sector is not a minimizer. It's not even a local minimizer, because it becomes unstable in the direction of the eigenfunction. If this is bigger than n-1, then this is local minimizer. Okay, and okay, the proof is just what I said. I told you before. And you could have, so this means that the critical point given by the spherical cup becomes more and more stable when this eigenvalue decreases. Other eigenvalue could pass below this threshold, so you get it becomes more and more unstable. Okay, so hence the conclusion is that when this eigenvalue is more than n-1, then there are hypersurfaces which are very close to the spherical cup, but in which the volume is the same, but the perimeter diminishes. And so we would like to understand this better, but anyway, when you take this direction, you don't know if you bump into a critical point. So you know just that the perimeter diminishes, and you don't even know if you bump into a minimizer. But are we sure that the minimizer exists? So the minimizer for the perimeter is not anymore the spherical cup, this is for sure, when we have this condition. But does a minimizer exist? And this is a beautiful result by Ritoré and Rosales in 2004, where using, in a very clever way, some concentration compactness argument, they proved that in any cone, convex or not convex, as long as the n-1 dimensional Hausdorff measure of the domain which spans the cone is smaller than the one of the alpha sphere, then the minimum is achieved. And it's regular, non-regular, according to the regularity of the minimum surfaces. Okay, so the corollary is that when you have this, and when you have this condition, which you are the one of the existence of a minimizer, then there exists a non-radial minimizer, which is not the trivial spherical cup. And actually, this gives you a non-radial constantly encouraged hypersurface, which intersects the cone orthogonal. Okay, so
Sorry. Can I ask a question?
The complexity prevents this condition.
Yes, and in fact, okay, I'll tell you in a moment. Of course, from this you deduce that the first eigenvalue for convex set must be greater than n-1. Otherwise, you get the contradiction. Yeah, in fact, it is true. I mean, you can deduce from here that it's too much. It was proved by Escobar and by Mazzio. If you have a convex domain on the sphere, then the first eigenvalue is strictly greater than n-1. So this is okay. So you may ask whether there are domains which have these two properties on the sphere. Yes, there are. So a nice domain is this, which is contained in an hemisphere. So you have a kind of sample domain. You can decrease the first eigenvalue if it is a tunnel between these two caps is small, or you can have a neighborhood of the equator. So for each of these two sets, you can produce compact culture surfaces which intersect the corner tone.
So the index is equal to the number of Neumann eigenvalues less than n-1.
The Morse index, yes. Yes. So this in principle means that you can have many, many more constant curvature surfaces when this reduced. One thing is interesting is that you see this condition here. Okay, this is very trivial. I mean, just take the measure, which is not bigger than half the sphere. So you can have plenty of domains. So this is an open question. So you can perturb a domain with this property, and you produce plenty of domains. And for all this domain, you have a minimizer, which is not trivial. So how do these surfaces look like? That's not obvious here. Geometers, much more expert than me, maybe. It would be very interesting to guess the shape of this one. It's difficult to think that they are, for example, a cylinder, a cylindrical. How do you intersect a cone like this of cone? Pretty strange, or even not having maybe enough geometric intuition. Okay, so let me just close with the final comments. The last one is the one where Luca was asking if this is convex, then this is greater than n-1. So when we have this property, we can have that the cone is non-convex. Okay, you can have, but the cone should be not so much non-convex. But what much non-convex means is not clear. These are Neumann eigenvalues. It's not so clear. Okay, so this would be interesting. So this seems that you could define an almost convex domain on the sphere just by requiring that lambda 1 of these is bigger than. So this could be a measure of the non-convexity of the sphere. But what classes of domains have this property? So this is greater. So this is the case when you have that the trivial solution, the trivial spherical is a local minima. But we do not know if it's a global minima. So this is an open question. So Figalli and Bayer proof seems to go into direction, but they do not reach a threshold. They just perturb a bit the convex cone. So it would be, so this is a very interesting question, but very, very difficult. And also another thing, you see, when you pass this threshold n-1, n-1 for the eigenvalue, then you pass from stability to instability, or from instability to stability for this spherical cap. So what happens when you are at this value? Okay, people who are experts in bifurcation could think that some bifurcation should appear. This would be very interesting because it means that you have bifurcation of constant mean curvature surfaces. Okay, so this means that you would have plenty actually curve of constant mean curvature surfaces, compact, intersect the cone orthogonally, and are not spherical cap. And it's a bit strange, they are very close to spherical cap. Very close, because if you have a bifurcation phenomena, then you are very close to that. Okay, so anyway, these are open questions. Okay, so this one I already have been commented, and that's it. Thank you for your attention.
Questions or comments? There are comments.
The two conditions there, not, I mean, lambda one is not monotone with respect to the size of the domain, no. We don't know, okay, these days I'm collaborating with Luigi Provenzano, with John. It's okay, I'm very, it's not, I'm very easy day. So, the normal value of the shear is not like the normal value of the plane. So even if you do some rescaling argument, it's not pass easily. I mean, some rescaling argument could be done, but it does not tell you that you how to deform the eigenvalue according to the rescaling. So they are difficult. The normal eigenvalues are difficult even in RN because we do not have the correct number of property with respect to many or other things like the no, so not even rescaling. Rescaling in the because in the real space, yes. Rescaling in the real space, yes.
Because you just
like 1 over square.
Exactly.
Yes, rescaling, yes,
But only
but not in general. But of the sphere, it's not clear what you will rescale because you cannot rescale.
For the case of equality with the n-1, it may be that the satisfies or not yet so there is equal.
I think, yes, I think this should be, you should still have the arithmetic integral, but as soon as you go down, it could be also possible that you have two arithmetic sides, this one and the other one. But I would think that for equal n-1, you still have it, but it's like when you have a minimizer, it's a semi-stable minimizer. And then as soon as you are passed to stability, then you lose this problem.
Thank you very much. Are there other questions in the room?
You know, some results the
What?
topology of the domain in the sphere is complicated if the index is large.
Yeah. I would be happy to have easily of the sphere and understand you would have even articles of the sphere with other things. Yeah. Yeah, so that's why I think there should be lots, many master living organizations.
I think that there are no questions on the web, and so are there other questions here? If not, we can thank again. Quindi ancora la medicina, grazie mille, possiamo stare. Arrivederci a tutti, buon pomeriggio.